right? Which is much simpler in a sense. It's much simpler. And then project 3 will be again a little bit more difficult, and then project 4 is up to you. Right? So kind of like it goes a little bit up, down, up, down. Of course, I hope that your final projects are really challenging projects, right? That you give yourself a big challenge, so it's exciting for everyone. Tuesday, May 1, today are the final project proposals due. So after class, we just get together very quickly. I mean, talk to everyone. You briefly tell me what you want to do. Okay, I read over your project proposal, and then if I have a question and cannot quite make sense of something that you say there, then I will ask you. You will clarify it, and then I will either say, go with it, that's it, sounds great, do it, or I will give you some additional ideas about how to make it simpler or to how to make it more difficult. Okay. So again, don't vanish. After class should go very quickly, maybe 1 minute per person or so. I just discuss a project proposal a little bit, and then it's resolved. So don't run away after class. I look at the proposals. The other issue is for the second project, you will run into the issue of having to solve linear systems of equations. Again, if you have your own little numerical library for solving linear systems, use it. No problem. You understand it. You trust it, right? You know it's robust. But by all means, you also are allowed to use any publicly available linear algebra package like LAPACK or MATLAB, whatever you are used to, whatever you have access to. I don't want you to have to develop your own numerical linear algebra package, but if you already have it, by all means use it. But otherwise, you can use public domain software. Talk about project 2. Talk about project 2. All right. So that's my assignment. Project 2, let's go over it. And let's pull it out so I can tell you what I really have in mind. Scattered data interpolation. It is due on Tuesday, May 15. So that's in 2 weeks, right? So in 2 weeks we will have the first demos, maybe all of them, because this project is so much simpler. Scattered data interpolation methods are needed to compute smooth representations, blah, 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 blah. Random locations are called sites, etc., etc. But I want you to do this project for the three-dimensional case, okay? Three-dimensional data sets, I mean, at least that challenge has to be there, but I will make it very simple. Three-dimensional case, I really mean trivariate case, okay? So your samples should be samples or sites in XYZ space with associated function values, f values, right? That's what I mean by three-dimensional. So your input data is of this form, four-dimensional tuples, xi, yi, zi, and fi, and you have n of those points. For the generation of meaningful test data, consider two types of input. Type 1, data resulting from sampling an analytical function, and type 2, data resulting from selecting a subset from any data set of your choice. So again, I strongly recommend that you start with a very simple function, analytical function that you know. F of xyz equals x squared plus y squared plus z squared. This is a very, very good one to start with. Right? So evaluate f of xyz equals x squared plus y squared plus z squared over the unit cube from 0 to 1, 0 to 1, 0 to 1 in all three dimensions, and then pick some random sites. Okay? Pick 100 points, pick 1,000 points, pick 55 points. Because you know exactly what you would like to get when you render it, right? You want to see concentric shells as contours for a data set that implies spheres as isosurfaces. And then once you have debugged your program and really understand what's going on, how you have to choose your parameters and so forth for a simple function like x squared plus y squared plus z squared, then I suggest that you also apply to something, say, the foot data set, right, or the skull data set. And again, how do you do it? Well, take a skull data set and you pick randomly 999 sites from the skull data set. And then you reinterpolate, approximate over the entire domain of that skull and see how well you can approximate the function that represents a skull by comparing it to the full-blown data set. So, but again, start simple and then work your way toward the real-world setting. Your program must support, emphasis on must support 4 scattered data interpolation methods. The global and the local versions of Shepard and of Hardy. So the Shepard method, the way it's defined on the assignment sheet, is really, I think, Shepard 2. In class I called that one Shepard 2. This is the one where you actually consider the function values only, the fi's, but you consider the squares of the distances. Okay? And I believe in the lecture I called that Shepard version 2, which will be smooth, but it will have these ugly flat spots. Okay? It will have plateaus at the sides, and you will see that. And Hardy is this approach where you need to solve a system of equations to get the unknown coefficients, the CI's. But above and beyond, there are two types of Hardy even. And one is related to this exponent plus 1/2, the square root, and one is related to this exponent minus 1/2, where you actually have 1 over square root of this expression showing up in the formula. And I really would like for you to deal with that as well. Okay, so the plus 1/2 version of Hardy is called Hardy's multi-quadrate method, and the one where the exponent is minus 1/2 is called Hardy's reciprocal multi-quadrate method. So your program should support both. So that actually means that you have to support 6, right? Six settings: Shepard and Hardy, local and global. And for Hardy, you also should consider the two typical exponents, plus 1/2 and minus 1/2. Experiment with these methods by computing in turbulence using different numbers of scattered data. So different numbers of scattered data is you compute an approximation based on using 50 sites, 100 sites, 1,000 sites. Okay, that's a different number of scattered data, a different number of samples that you feed into your approximation. And you compare the results using the different results that you obtain from the different methods, blah, blah, blah. And then there is this one parameter, r squared. I didn't talk a lot about r squared, except saying maybe that it's enigmatic or hard to understand or mysterious. R squared is this parameter that shows up in the matrix that you have to deal with. That you have to use either for doing a Gauss-Seidel iteration to come up with a solution, or that you have to consider when you do a Gaussian elimination or any other direct method to do matrix inversion. And I just printed this so you see that there is this thing called a diagonally dominant matrix. Right? Matrices have certain properties. And a matrix is good, or some matrices are good, that are at least dominant with respect to their diagonal, right? A matrix that is diagonally dominant is a matrix where the absolute value of the entries along its main diagonal are all greater or equal to the sum of the absolute values of all the other entries in the same row. Okay, that's a matrix that is diagonally dominant, and this matrix is good for certain operations that we do on matrices. Turning that around, when you actually choose the r squared in such a way that the resulting matrices are very far away from being diagonally dominant, then you can have all kinds of ugly numerical problems when you use an iterative scheme to solve for the unknown coefficients. Okay, numerical instabilities in general. So therefore, you should think about that, what that means, coming up with a good r squared. There is no optimal r squared. There is no best r squared. It's a data-dependent parameter that ultimately will depend on the distribution of your sites and the geometry of the sites, the coordinates where these sites are in x, y, z space. Okay? But again, I gave you this little hint. There's a relationship between a good matrix, which is a diagonally dominant matrix, and the geometry of the sites. And diagonally dominance means you just want to make sure that the stuff in the diagonal is as large as it possibly can be relative to the other entries in the matrices. Okay, that's the best you can hope for in the Hardy method. Choosing r squared in such a way that the diagonal elements are relatively large compared to the rest of the stuff in the matrix. Okay, that's all I want to say about that. R squared is another parameter with which you can play. The number of scattered data to be considered is a parameter that you have to consider when you compute local approximants. Okay, so the localization, is the localization clear to everyone? What it means to do a localized version of Shepard and what it means to do a localized version of Hardy? Is it completely clear to everyone or not 100% clear? Okay. What do I need to do? What is the basic operation? The basic operation is I want to compute a data set that is of resolution n by n by n at the end of the day, right? I want to compute a Cartesian data set. I want to sample my approximating function on a Cartesian mesh. 256 by 256 by 256 samples, evaluation locations where I evaluate the approximating function. And therefore, I have to evaluate at all these ijk locations, ijk from 0 to 255, I have to evaluate the Shepard function and the Hardy function at all these voxels, right, inside my unit cube. Whenever I do that, whenever I want to approximate a value at a particular voxel location, ijk, I need to compute the value of Shepard or I need to compute the value of Hardy. Right? That's the basic operation. And whenever I do that, for Shepard, I have to compute these huge sums. In order to make the sums smaller, I just consider 5 data close by. So when I have to approximate a value or evaluate this approximating function at a particular voxel location ijk, I only will consider the k closest original sites that I have in my scalar data set. The k being between 5 and 15. It's a good number, right? Maybe not. You choose the k closest ones to evaluate Shepard. And then this huge sum is not a sum over 1,000,000 sites, but just a sum over 10 or 20 sites. So it makes it much faster. With respect to Hardy, for Hardy, you always have to solve a linear system of equations, right? That means when you do a local version of Hardy, and in order to evaluate your Hardy function at a particular voxel, ijk, you also need to compute the coefficients ci in this Hardy expansion, right? That means whenever you move around in your voxel space and you need to compute a new voxel value, for each new voxel location ijk in the unit cube, you have to set up the matrix, a k by k matrix, right? If you use k local sites, and you have to set it up and you have to invert it, right? To get the solution for the coefficients to approximate as this particular voxel value. That means for all the voxel locations for which you need to approximate function value, you have to set up the big small matrix. You have to set up a smaller matrix. You have to iterate it, or you have to invert it directly to get the coefficients for the expansion, and then you evaluate that resulting h, capital H function at that voxel location, right? So, all right. So far, so good. I hope that made sense. Again, jump in there if it doesn't make sense. Regarding the visualization, should we talk about visualization next? No, let's talk about the data structure. So there is this big issue of speeding things or making things fast when you localize. Independently of localizing Shepard or localizing Hardy, you have this query given a particular location in space, right, where you need a function value. Determine the k closest sites, k being any positive number. So the brute force method to do that is you do not set up a data structure to help you with that, but whenever you evaluate at this particular location, you always just compute the squared distances to all the sites you have, and among those you pick the 5 closest ones if you want to use the k equals 5 closest ones, right? You have to do that all over the time. It's very expensive, right? So the other way to do that is to actually use a very clever, efficient spatial data structure like an octree, right? That can help you significantly to speed up the searches of the k closest points from a given point set when I'm given an arbitrary location x, y, z. Now, again, there's a trade-off. That spatial data structure octree is hard to define as an object, as a structure, unless you already have implemented it. And it's not that easy to traverse or to query or to use for a particular purpose. Anyway, some of you might already have a working octree structure lying around, so by all means use it. Some of you might want to try for the first time to implement a good octree structure for the first time. By all means, do it if you want to do it, and you get bonus points for that, right? So in the worst case scenario, of course, is you just do everything brute force. You do not use the spatial data structure, but whenever you evaluate at a particular location, boom, 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 for every evaluation step, you determine the 10 closest sites, and you do your Shepard thing or you do your Hardy thing, right? That will be slow, and that's not the way you would do it in a real system, but it will solve your assignment, right? So you can do that. There were two questions. First.
Yeah, so on the last assignment, we used data from the Volviz website, and if we use that data for this assignment, since it's on a regular grid, we wouldn't have any advantage of using a data structure to find nearest neighbors. So can you recommend a data set that isn't on a grid like that?
On what measures are you thinking about?
So, I mean, because it's the data is evenly spaced, and it's on a rectilinear grid on Volviz, there's no reason, I mean, it is a data structure in itself for determining the nearest neighbors.
I think the idea is to take random samples and interpolate their function values from those data sets.
Yeah.
So even though they are, a perfect volume or for perfect cube or whatever, you interpolate n samples at different locations in it, and those are your random samples, and you use that with Shepard's or Hardy's method. So when you have those random samples, you no longer have the perfect data structure. You have a set of random points or a cloud, and then that's why you would need to do the arc tree or whatever.
Yeah. So Nick explained that. Does it make sense?
Well, I'll just have to look at my notes again then.
No, it goes to the assignment. What I mean by I just went over it. Obviously, I didn't explain it though. So when you have,
I understand why you would use data structure, but I thought the points are already.
So the regular structure goes away, right? When you have a regular structure, a Cartesian mesh data set of 68 by 68 by 68, you forget that.
Yeah, that was.
You just pick randomly. You pick point 14, 14, 14. You pick point 77, 48, and so forth. And you pick 100 random voxels from this Cartesian meshed data set, but then the whole nice structure is gone afterwards. Right?
So your cube has holes in it, and it has more holes in it than you actually have data because you're taking that small a sample. And on that site, there's stuff that is different pitch. So you can get something that's like 3 step in one direction, 0.8 step in another direction,
that actually having.
So I want to make sure that this is understood. If there's no clarity about this particular point, because it's a very simple point.
When you
just
take
pick
the samples,
100 points, right? It completely doesn't matter from what kind of mesh they come, whether it's a structured mesh, an unstructured mesh, a Cartesian mesh, a rectilinear mesh. Doesn't matter. You just pick 100 points, meaning 100 XYZ locations with a function value there, a density. Right, that's it. Once you have chosen 100 sites, locations, geometry plus function values, you forget the whole notion of structure or mesh altogether. You only have a scattered data set, 100 points, 100 tuples, x, y, z, f, I from 1 to 100. That's it.
Yeah, but I mean, can I use the original mesh to help me know who my nearest neighbors are?
No, I don't want that. No, you should not do that. No. Yes, of course you could, but I don't want you to take advantage of that. Because the general setting is you start with random sites, with random locations, with scattered data.
Yeah,
you do not have access
what
to
I was wondering is if you had a data set that is like that, because then it would feel most useful to use such a data set.
Okay. Well, if you can figure that out and can convince me that if you know that your random 100 samples coming from a Cartesian mesh allow you to accelerate things by making reference in some clever way to the underlying Cartesian mesh where they come from, fine.
Okay.
Okay. If you see some link there, some relationship, some cool trick that one could possibly use and think about, yeah.
So when we do pick our samples, they don't just have to be voxel or locations at a voxel. You could interpret, or do use the trilinear interpolation like we did, or that we made for the first assignment, and pick, so-called.
You can
Okay.
do that.
And when you pick the sample, is it, for example, 100 of them? Is it should be excluding all the zero values?
Pick them randomly. I mean, you can pick them in any way of your choosing, right? You can choose them randomly. You can choose them in such a way that they will be uniformly distributed with nearly uniform density and distribution. You can choose them in such a way that in half of your cube you have twice the density of samples than in the other side, so you see that what the effect of density of the sample says, or whatever. Just choose 100 points. Okay. So these are other effects. I mean, of course, if you do your sample selection or your sampling in some bizarre ways, that will have effects on the resulting quality, right? But that helps you to study the quality of the resulting approximation, right? In part of this room, use twice the density of sites. In the other room, use half the density of sites. In one half of the room, use a rather structured arrangement for the sites, that the sites are somewhat regularly placed in space. And the other one, do it completely randomly, right? So you can play all kinds of games. If samples come in certain ways, certain densities, certain distributions, certain structural arrangements, certain patterns, I see that Shepard and Hardy behave in certain ways, right? You can derive conclusions. So you can play with that. Nick?
Sorry, I was just moving it away so they improve.
Everything clear? Okay. Visualization. Regarding the visualization of scalation, I advise you to keep things simple, evaluate the interpolants on a uniform rectilinear grid, Cartesian grid, n by n data in a unit cube, and allow the user to perform grid plane slicing, right? The simplest visualization technique there is. And shade the cutting planes based on the function values at grid points, and just use Garot shading where you interpolate the color values at the four corners of a quad inside the cut plane using some predefined color map, right, for the function values. Or if you want to do that, I'm just making this suggestion, you might want to consider raycasting of the volumetric data, because by now you have your raycaster, right? And if you trust it, but only if you trust it, okay? And if it's fast enough, of course, then you can also raycast your approximation based on Shepard and based on Hardy. But I will be happy if you just support this functionality, okay? One cut plane has, say, 512 by 512 pixels in it, and you slice it, right, in this particular coordinate system plane, in the xy plane, you slice it in the xz plane, and you slice it in the yz plane. That's all I want, okay? I don't even ask you to do arbitrary orientation and cutting through them. No, just very simple cutting. The three basic coordinate system induced slicing planes. And then you do Garot shading of the quadrilaterals in that slicing plane based on the function values and the color map that you define. Rectilinear grid, perform grid plane slicing, or use ray tracing. If you trust your ray tracer and it's fast enough, then you can also show me raycast images. Besides having to demonstrate, give me again one of those very short, simple manual sheets where you show me how to run your program, what the parameters are, and so forth. Additional credit. Yes, if you want to fool around with the samples, I mean, how Shepard and Hardy respond to different types of densities, distributions, and sample patterns in the sample locations. By all means, do that. If you want to establish some kind of fast lookup or fast k-nearest neighbor searches based on taking advantage of some originally known Cartesian mesh from which the data come, do that, okay, by all means, if you see that there's some value there, and play with that. And the other issue is, I said for Shepard, you only consider the function values. But I already told you that that's not good enough in general, because then you see flat spots. The pictures will look blobby, okay? It's not smooth enough. So therefore, I gave you Shepard 3. Shepard 3 also uses gradients, right? And so if you want to do that, then go to Shepard 3 and actually construct gradients and linear linear Taylor expansions at the sites and interpolate the linear Taylor expansion. You will get much better results. Okay? You can do that. And alternatively, and I will talk about that a little bit today, or I will begin talking about that today, you can also use tetrahedral meshes to actually do a tetrahedral mesh-based approximation. Okay. Any other questions? Is it all clear? Again, most important advice, start with simple functions that you understand, right? Use samples from a very trivial function, x squared plus y squared or z squared was the one that I always used to begin anything. And then if my implementation of something produced somewhat meaningful pictures, then I could actually trust my implementation, right? And then I actually apply them to more complicated stuff. Otherwise, I cannot really trust anything. If I cannot even convince myself that I can reproduce spherical shells, right? So, and on those spherical shells, you will see all these ugly problems with Shepherd, because Shepherd has flat spots, so it will not produce the nice spherical shells, no matter what, right? Only in the limit when you go to higher and higher numbers of samples, then it will get better, but still you will see jumps or ugly step effects in there, because those plateaus will never go away. Okie doke. There's project 2. Just put this away. The next topic is concerned with triangulation-based or simplicial complex-based data approximation. So these themes that I talked about so far, Shepherd and Hardy, have this great advantage that they do not require one to establish a connectivity among the sites, right? You just have locations with dependent variables. That's great. You don't have to worry about a data structure. You don't have to store a complicated data structure. You don't have to update or query a complicated data structure, except maybe for the evaluation when you need an octree to actually speed up the evaluation. But for the original scalar data set, there was no structure, there was no mesh, there was no grid. And that saves storage, right? But maybe it is not so good after all, because the resulting approximations aren't as great in terms of quality as you would like them to be. And so that's what the next topic is really about, to use triangulation-based methods to improve the overall quality, numerical quality of the approximations one can get. So therefore, what is my thought process? What do I want to talk about today? First, I want to talk about triangulation a little bit. Okay, how many triangulations there are, which ones we pick, and when a triangulation is good and when a triangulation is bad. That all depends on the purpose for which one actually wants to use a triangulation, probably, right? And then triangulation, what comes next? Triangulation, I have to talk about triangular patches, okay? A triangle itself will imply a linear polynomial. 3 points, a triangle, a linear polynomial. That will be the most primitive of approximations. We have a triangulation and a piecewise linear polynomial approximation living above that triangulation. That will not be good enough. We want to make it better, smoother. Right? We want to use curved patches, curved functions, continuity of higher degree. So I have to talk about patches, triangular patches and simplicial patches. And when I talk about triangles, our whole notion of x and y and right angles will go away. Okay, it will destroy that. So we think in terms of right angles, right? X direction, y direction, and there's a right angle. So the triangle is a different beast, and so therefore a triangle has a different inherent coordinate system, which is related to its own geometry. And so I have to talk about barycentric coordinates to introduce a way to describe functions living over triangles or simplices in general that are based on a parametrization which is inherent to that particular object. It's no longer related to the perpendicular coordinate axes of our typical Cartesian coordinate system. So I have to talk about barycentric coordinates. Once we know that, then I have to talk about curved patches over triangles and curved hyperpatches, call them that, that live over tetrahedra, right, for the volumetric setting. And after that, I have to talk about high degrees versus low degrees. And when a degree is good enough for our purposes. So the issue is higher degrees allow us to reconstruct functions better and better in terms of their smoothness. High degrees also have the unfortunate effect that they will lead to oscillations. We don't want to have those. But we do not just want to have piecewise linear approximations, because that's not good enough for graphics or rendering, because whenever we have jumps in gradients or jumps in normals, our eye will pick those up, and it will lead to, right, all kinds of effects where we will see discontinuities. And if these discontinuities are not supposed to be there as part of the phenomenon, we have to smooth them out. So we need some higher level of smoothness. The question is, what degree do we need? Quadratic functions are good enough, or cubic functions, or do we need quintic functions? What's good enough? And again, when we go to polynomials of degree 10, things will start to wiggle and to oscillate. We don't want that either. The other issue is there's a great technique in computer graphics which allows you to produce beautiful images, and this technique is called ray tracing. Right? The basic function or operation that a ray tracer has to do very efficiently, is to compute intersections, right, between the rays and the objects. Okay, and you remember that from your ray tracing assignment, right, in Introduction to Computer Graphics, that all the objects you use for a ray tracer are usually of what degree? Up to degree 2. Quadratic surfaces. Why? Because then the intersection problem still becomes the solution, or relates to the solution of a quadratic equation between the ray equation, a line, and the quadratic surfaces. Okay, and you get two roots. So therefore, for rendering purposes and for very effective direct rendering purposes, quadratic representations are ideal. As soon as you enter the world of cubics, you can no longer solve the roots of a cubic polynomial in one step. There's iteration necessary. And so you want to avoid that. So then the question is, okay, I want a high degree of smoothness because certain physical phenomena will force me to use high degrees of smoothness. At the same time, I would like to stick to quadratics because the quadratics are good for using computer graphics and ray tracing, right? So there will be this balance, and I will talk about. I will try to make the relationship between these different things obvious. All right, so let's start with triangulations first. Triangulation-based methods. Triangulation-based methods. Scattered data approximation methods. Data approximation, approx methods. Okay. So what is the setting? The setting is I illustrated for the 2D case. And in your mind, you can extrapolate all of this to the volumetric setting. So we have sides. And I say the method to construct a smooth polynomial living above these sides where we have function values should be based on a triangulation. So is this triangulation given to us? Sometimes it is. But in the general setting, it is not. If people do sensor networks and measure temperatures in this room, so there is no inherent triangulation. You have to establish the triangulation. How many triangulations are there to triangulate this point set? So first, is there a boundary? What is the boundary of a point set? Maybe we start first with thinking about the boundary of the point set, right? What's the boundary? And then we think about the triangulations. Well, this is what I want, right? I want something like this. And then we have to think about what it takes to get there, right? This is a good boundary? Looks like a good boundary, right? And then a triangulation, I want something like this. Does this look reasonable? Looks good, right? Looks good. Why is this good? Depends on some criterion, right, that I have in the back of my mind. So, therefore, I need a good triangulation. Triangulation. Okay, and so these are just remarks. I do not want to go into the whole issue of triangulating data sets because it's a topic in its own right, and it's part of computational geometry. But there are some remarks. There's a very famous number in combinatorics that is related to the number of different triangulations you can get. The different number of triangulations that exist for a convex polygon to be triangulated, and that is the so-called Catalan number. You remember that, or have you heard that? Okay, so these are just remarks. This is a Catalan number. Catalan number. It's called Cn, and it's maybe a big number. It is, if I remember this correctly, 1 over n plus 1, and then it's some kind of combinatorial thing. It's 2n choose n. Okay. This number probably goes very quickly with n going up. You can compute a few of these. And Catalan number. I don't want to give you the whole thing, but the Catalan number is related to the number of distinct triangulations for a convex polygon. And that number, in turn, is related to the number of triangulations needed for points that also have interior points. Okay, there's a relationship. So essentially, the number of triangulations for a point set like this is related to the Catalan number, which gives you an idea how quickly the number of possibilities grows. Okay, so you cannot possibly explore all triangulations. The number is just too big. So let's say it's related to the number of possible triangulations. Possible, and triangulations, I will just write it like this, okay? Triangulations. Okay. This number is pretty big already for n equals 10, okay? So then you run into this problem of boundary, right? What is the boundary of a scattered data set? Well, the sites. We want a boundary for the sites. Need a notion, need a boundary. Notion of boundary of all the sites. Okay, again, this is a topic of computational geometry. So I just allude to it. If I give you sites in the plane, then what is a good boundary? This is a good boundary, right? What is that polygon? It's a convex polygon, yes. And it's the boundary polygon of what set? The convex hull of that point set. There's a bunch of points in here, right? So this is a boundary polygon. Boundary polygon of the convex hull of the set of sites in our context, set of sites. And again, there's always the confusion. The convex hull is just this polygon. No, that's not true. The convex hull of a point set is this convex region, okay? This region, the shaded region, is the convex hull of the point set. And this is just the boundary of that convex hull. right? So all these points are points pi, and so this convex hull CH, right? It's called convex hull CH. CH is usually is a set of all points P that can be written as a combination I from 1 to n. There are n points with weights of all the given pi's, weight I, pi, such that these are convex combinations, meaning that all the weights are positive and sum up to 1. 0 smaller equal any weight, smaller equal 1, logical end, the sum of the weights has to be 1. Sum of all the weights has to be 1. I mean, again, this goes back to computational geometry, and I don't want to talk about it too much. But the main point is there is computational geometry, there is something like a convex hull, and there is something like a boundary of the convex hull, which in 2D is a convex polygon, and in 3D it's a convex polytope. And you need to compute these boundary things. And there's also a nice algorithm to compute this. You remember that? How that algorithm works? Did you ever compute the boundary of a convex, the boundary of the convex hull of a point set in 2D? Okay, it's called gift wrapping algorithm. Okay, a very fundamental, very important algorithm. I've never done that. I suggest to implement it just for fun. Just do it tonight to have some fun. And so the way I do it is I take the leftmost point. Okay, it's very simple to actually. You take the leftmost point. This is the leftmost point. Then you use the leftmost point as the center of rotation. And you rotate this infinite line about this point until it hits another point. So if I rotate this guy around until it hits the next point, it will hit this guy first, right? So I rotate this stick, and I rotate it until it hits the next point. It will hit this guy. Boom. Well, then this next guy, this was my point 0. This will become my next point, my point 1. Then now I use this point as the center of rotation, and I rotate this line about this center of rotation until I hit a point. If I always allow myself to rotate to the left, mathematically positively, then I will hit this guy next. So I will hit this point. This one then will become point number 2. Now I will rotate this line about this point until I hit a point again to my left. The next point I will hit is this guy. Then I will rotate about this center of rotation. I will hit this guy. I will rotate about this one. I will hit this one. And then I rotate one more time until I hit back to the first point. That's gift wrapping, right? That's how you wrap paper around something. And you get this. And so this is then P n minus, or K minus 1, whatever. K minus 1. K points defining the boundary polygon. It's very neat, right? Take any line and then always rotate to the left. Click, 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 and you hit, right? You always hit a point with the one that you hit next. Ultimately, you come back to the beginning. Very cool. If you don't want to do it so beautifully, this is a gift wrapping algorithm. Gift wrapping algorithm. Then there is a more brutal way, or more crude way, of defining a boundary, a meaningful boundary for a scalar data set. Another meaningful one is just use a bounding box. Take the left point, take the right point, take the bottom point, and take the top point, and that's your domain, okay? Just do that. And then you just evaluate things in this region. Okay. So bounding box alternative, you always have that. The cheap version. The gift wrapping in 3D becomes much more complicated, right? Obviously, if I give you a bunch of locations, sites, where you have sensors in this room, and you do this, you wrap it, then you will get a polytope, right? With a bunch of, in general settings, triangular faces. So think about that. That's cool stuff. So you need the boundary of the sites. Now you need to worry about the triangulation, once you have the boundary, that isn't everything that you need, right? You also need to establish the connectivity among these guys in the interior of this domain. So that goes to this note, or this issue of what is a good triangulation, right? What is a good triangulation? Because there are so many. Which one do I pick? Good triangulation. Again, this is a huge topic in its own right, and it's studied in approximation theory as well as in computational geometry. So, one triangulation of a point set is unique, generally speaking, and that this triangulation has a beautiful name, and it's called. Come on, you've heard about it.
Delaunay triangulation.
The Delaunay triangulation, right? Or Delaunay complex. So, Delaunay triangulation. It's unique and it's the best in some sense. Okay? So if I give you 4 sides, then what is the Delaunay triangulation of this quadrilateral? Is it this one? Or is it that one? Right? I give you the same side set twice, and so there are 2 ways, right? To triangulate this A quadrilateral, you can either triangulate it this way or you triangulate it that way. Which one is Delaunay? Okay, I make it more obvious. This one and the other is this one. Which one is the Delaunay triangulation?
The one on the left.
The one on the left.
Tries to
right?
avoid skinny triangles.
This one has skinny triangles, this one has round triangles, okay? And we like round triangles. Okay, this is better. This is Delaunay, the other one is not. This is a Delaunay triangle. This is not Del, okay? Because there exists one that's better, namely the one on the left. So, Delaunay wants nice triangles, okay? Nice triangles. And what means nice triangle? Nice triangles means that you would like to maximize the minimum angle considering all the angles of your entire triangulation. That's what it does. The Delaunay triangulation is Delaunay if it maximizes the minimum angle of all the angles in your entire triangulation. So a Del triangulation is it's called a so-called max-min triangulation, max-min angle triangulation, i.e. it maximizes the minimum angle. It maximizes the minimal angle in the triangulation. Okay. Is the Delaunay triangulation always unique or is it not? Note. Okay. If I give you a nice, happy square, this is a square, okay? Then how many Delaunay triangulations are there for a square? Come on, follow your intuition. 2. They are equally good, okay? For the square, of course, this is a Delaunay triangulation, but the other one is just as good in terms of the angle behavior, the angle quality, right? So, therefore, when the sides to be triangulated are not in what is called general position, you have degenerate cases where there are multiple optimal solutions for the max-min problem. You get multiple Delaunay triangulations. Okay, So note, when points are not in general position, then you can have non-uniqueness. A del triangulation is only unique for points or sites, for points in what is called general position. And that's all I can say. Look that up in the computational geometry literature, what that means. What is a good triangulation? There's a Delaunay triangulation, and then there are many other triangulations. There's a very important one in our context of data approximation, because this criterion, the Delaunay criterion, is only interested in the beauty of the triangles, but it doesn't consider at all the approximation, the function value. We are interested in the quality of the approximation, right? What am I concerned with the beauty of the triangles and having big angles? It doesn't matter, because over these triangles I will construct a function. I'm interested in the quality of the function that lives above the triangles. I don't care about the inherent geometry of the triangles themselves. So there's another very important one. And so important people you have to read the literature from is this guy, Adelsbrunner, and also Lawson. Adelsbrunner, Lawson. There's another one which is very important. There is a so-called, there is a dependent triangulation. And that is important for data approximation for our purposes, relevant for data approximation, function approximation, data approx. And you have to read the literature from Din, Levine, and Ripper. And there are many, many other triangulations that are good triangulations needed for non-convex domains, right? All of this, there's a convex boundary. You also need to construct functions that are defined over non-convex regions. Triangulation needed for non-convex regions. Non-convex regions. So you need to worry about constructing triangulations for regions which have a non-convex boundary or outline. Non-convex region. Triangulation for non-convex regions. Right? So if you have a sample set like this, right? Maybe you want this to be the boundary, right? And not a convex. So you need to worry about that. When you want to have a triangulation approach, when the boundary polygon is non-convex, and you want to establish a triangulation that will not introduce any edges lying outside this non-convex boundary polygon, right? So you have to worry about that. And there's much, much more just to the topic of triangulation. So now we just assume we have triangulation, and we need to construct functions over the triangles. Our purpose we construct functions over triangulations. Functions over triangulations.
Sir?
Good.
I have a question regarding triangulations for non-convex regions. And perhaps this is a naive question, but couldn't you just divide it into sections and create convex regions
Yes.
and concatenate them?
Yeah. Right, you can do it. the union of any non-convex region, any non-convex region can be written as the union of convex regions, right? So you can cut it here. Yeah, but the question is then, how do you find those? Yeah, all right. So functions over triangulations. We have our sites. And we have our function values. And if we have a triangulation, at this point we have a triangulation, right? At this point we assume that somehow we have established a triangulation. And here are our sticks above the plane, coming out of the plane. So what is the simplest function we can construct over this triangulation? The simplest function is given by the triangles that live in space, right? That are just made up by connecting the original sticks based on the underlying triangulation of the plane, right? That's a piecewise linear function. So is this nice? Is this good enough? If we do this everywhere, it looks like a tent, right? There will be discontinuities in the normal, so it's not good enough. But the simplest solution, of course, is simplest is a piecewise linear function based on linear polynomials implied by each triangle in the domain, in the xy domain. Simplest, the piecewise linear function induced or implied by the triangulation itself. Okay, so then what is the inherent form of one of those triangles or triangle pieces for this function f of xy? Each one of those function pieces, there will be many of them, namely as many as we have triangles, will be of this form. It's always an a plus a bx plus a cy, right? And we have as many linear pieces as we have triangles. But this is not smooth enough, right? For our purposes, not smooth enough. All right, we want something that is smoother, so I have to talk about smoothness. And we have to understand smoothness only along the edges and around the shared vertex. That's all you need to understand, what it means for one of these representations to be smooth along the edge and around the vertex. So right now we have this setting. We have two triangles and we have function values above them. These are the sides. Function values go up. And so the initial approximation looks like this. It's just this polynomial. Right, a linear polynomial on the left, a linear polynomial on the right. And the issue will be that I have one normal for that triangle when it comes to rendering, say, that goes in that direction. I will have another normal that goes in that direction. Where do I have a discontinuity? The discontinuity occurs along the edge of the triangles, right? I don't like that. So therefore, I have to understand how to make this smooth. Obviously, linear pieces won't do it. What do I want? I want something like this. Wanted. So this is the bad situation. For most applications, not good enough. Wanted is a representation where I have a smooth curve in the middle, and I have something like this, something like that, something like that. Now I can go down here. Side, 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 value, 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 value. Right? You get the idea that I have curved pieces living above the two triangles. And so the important part is, this is still my xy domain, and here's my f function direction. Here I have a smooth transition from the left piece to the right piece. There's no normal discontinuity, but the normal on this shared edge is unique whether I approach this edge coming from the left or whether I come from the right. Okay? The normal changes smoothly over these two pieces. So this is a smooth normal along edge. Smooth or continuous. Smooth normal or gradient later on. Normal slash gradient, gradient along edge, along the shared edge. That doesn't suffice just to understand what has to happen along a shared edge. You also have to understand what has to happen around a shared vertex also. So how can I sketch that? I guess I can sketch it like this. And then, okay, so you also have this situation where you have three patches coming together. In general, an arbitrary number of patches can come together at a shared vertex over the triangulation domain space. X, Y, F. Side, 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 and side. And so now you see in the domain I have three triangles, right? 1, 2, 3. And over each triangle I have a curved piece, a curved patch. And so now there's this one vertex, this vertex in the middle, where three, not just two, right? It's always two neighbors, two triangles, right? One edge is shared by exactly two triangles. And at most two triangles, unless you live on the boundary of something. But a vertex can be shared by an arbitrary number of patches going around it. And that's the ugly part. And so this also has to be a point where all the normals coming together at this shared corner are the same. With the other case, it has to be satisfied besides the edge continuity. So you need the continuity along edges, which always involves two triangles and not more. But here you have to deal with an arbitrary number of triangles that all have to have the same normal where they come together. So all triangles sharing a common vertex, or corner must have same normal slash gradient there. Must have same normal slash gradient at this vertex. So that's what we are after, constructing these curved pieces which produce something that is overall smooth. Now I cannot draw the pictures for the volumetric setting, of course, right? I can only draw it for surfaces over the plane. There's also thinking about this now. You triggered me thinking about this. There's a so-called rolling ball algorithm to get a boundary definition of non-convex regions. A rolling ball algorithm. Think about that. What might that mean? You have a marble, a certain baseball, soccer ball, whatever, and this ball rolls along this point set. And if this ball has a certain diameter, then it will help you to trace out this boundary, which will be non-convex. Think about that, right? The algorithms to do that are rolling ball algorithms. Again, it's computational geometry. So you need that, for example, for meaningful definitions of molecules. When you have positions of atoms and you need a meaningful definition of the outer shape, the outer boundary for molecule, you also have this problem of having to construct a non-convex boundary. And then people have like rolling spheres, rolling around, tracing out these molecular surfaces. Very, very cool stuff. So now I lost my thought. No, now we need the notion of remark of barycentric coordinates. We need barycentric coordinates for a good notation of triangular or triangulation-based functions. Triangulation-based functions. Okay. So I will do this very carefully with the barycentric calculus and just build it up from the 1D case to the 2D case to the 3D case. In the 1D case, I have a line. I call this line the x line. On this line, I have 2 points. They are our sides, side 1 and side 2. I call it x1 and x2. And now I have an arbitrary point, this guy, which will be my location x. And now in barycentric notation, I can write this point x as a combination of the other 2 points. Usually you think of x being the ordinate or the x-axis, and you just measure things as 0, 1, 2, 3, 4, 5. But in the context of barycentric coordinates, you take 2 reference points on the axis, and you represent an arbitrary location as a combination of these other 2 fixed points. So then you can say x is a combination of x1 plus x2 with certain weights in front of them. And these weights are their barycentric coordinates, u1 and u2. And do you remember what they are? This whole interval has some length L. The left piece from here to here is call it L1, and call the right piece L2. And now it's coming back to you. U1 is what, and U2 is what? The left point gets multiplied by the right interval, and the right point gets multiplied by the left interval. Okay, that's linear interpolation. And barycentric coordinates are related. So U1 is, well, then this notation is wrong because you always index with the opposite around. So the right one is L1, and the left one is L2. So you can say U1 is L1 over L, and U2 is L2 over L. Okay, that's for the 1D setting. Now we go quickly to the 2D setting, where you have in the 2D plane, xy plane, you have 3 reference points that define a triangle. And this is a more common way for you to think about it, I guess. So the points then are, and now I call them points, boldface notation, right? I use this for boldface because you have xy component. This is an x1, This is an x2 or point 2. This is my point 3, x3. And now I want to have an arbitrary point somewhere inside the triangle represented as a combination of the 3 points. You remember that? So here I had length. In the case of a triangle, I have areas, right? So then this is point 1. Then the opposite triangle is area 1, okay? This is called area 1. So this is point 2, so this is area 2. Point 3, this is area 3. The entire triangle will have area A. Right? That's just going from the 1D case now to the triangle case. So now we can write this arbitrary point here in the middle, call this point x now. Okay. And I can say this arbitrary point x is now a combination of the first point plus something times the second point plus something times the third point. And again, the weights are the same u's. It's a u1, a u2, and a u3, where ui is what? Ui is just an area I, divided over the sum of the areas, a1 plus a2 plus a3. It is just a barycentric representation of an arbitrary point in the plane with respect to 3 base points. Okay, so now we can also do that for 3D. 2 points, 3 points, 4 points, line segment, triangle, tetrahedron, right, a tet. And that's what we will need later on. So in 3D, the situation is I can only sketch the geometry of the element. The element then is a tetrahedron. With its 4 corners, our sides in 3 space later on. And I need to represent an arbitrary point somewhere in the middle or somewhere in the interior of this set with respect to the 4 corners. So again, I have to connect. I do connect this arbitrary point to the 4 corners, and this way to split the tet will split it into 4 child tetrahedra, right? Huh? A line gets split into 2 children. A triangle gets split into 3 children. A tet, by splitting it this way, will get split into 4 child tetrahedra. So then I have my first point or corner, point 1, point 2, point 3, point 4, point 4. And here's my arbitrary point, point x. And I will be able to represent x as a combination of something times corner 1 plus something times corner 2 plus something times corner 3 plus something times corner 4. Okay, what are the things, the weights, the coordinates, barycentric coordinates in front of it is u1, u2, u3, u4. And where you have what? U sub I will be the volumes, the subvolumes, the volumes of the child tetrahedra relative to the entire volume of the parent tetrahedron. So ui is vi over v1 plus v2 plus v3 plus v4, where vi is a subtetrahedron's volume. Subtetrahedron's volume. So this is just this switch to barycentric coordinates. So the ui's are the barycentric coordinates, barycentric coordinates of a point x. Okay. Now, usage of barycentric notation. Notation. And I do this for Bezier-Bernstein, Bernstein-Bezier polynomials, Bernstein-Bezier polynomials. So, example, quadratic Bezier curve. And you have seen this already in the Raycasting example, in the case of representing voxels with cubic Bernstein-Bezier polynomials. Now I go back to just a quadratic case. You remember, I can just represent such a function by calling these fixed Bezier ordinates b0, b1, b2. And then I can write this function as a function f of x, which is just sum I from 0 to 2, 2 for degree 2, 2 for quadratic, of these coefficients, or Bezier coefficients, Bernstein-Bezier coefficients bi, times these Bernstein-Bezier polynomials, bi2 of x. That's the way I had talked about it before. And now I changed this notation to expressing everything, not with respect to just this abscissa, but with respect to barycentric coordinates. Now I changed this, change notation to barycentric notation. Barycentric notation. And again, why do we have to do this? Because we will be dealing with triangles. And the triangles are inherently not like the xy coordinate system, but the triangles require us to think in terms of different coordinate systems, namely the barycentric coordinate system. So I show you how this one changes when I write this in barycentric form. This is still an x-axis. This is our space. And this is still our f. But now the sticks would have different names. They would have two indices. So this stick will now be called b2, 0. This one will be called b1, 1. This one will be called b0, 2. Why is he making things so complicated when it could be so much simpler? Well, it's the same curve. But now I write this curve as a function f of two variables, because now I want to express any point on the x-axis as a combination of the left point, point 1 and point 2. And when I talked about representing any location on the x-axis as a combination of two other points, all of a sudden we needed to use a u1 and a u2. So that's the switch I'm doing now. I'm going from a notation that uses just one argument or one parameter to a representation of a one-dimensional manifold, a curve, using two parameters by switching to the barycentric calculus. So when I do that, then I write this thing in terms of this u1 and u2 tuple, and then the sum also changes. The sum becomes the sum I1 plus I2 equals 2, and I1, I2 greater equals 0 of b I1, I2 times 2 factorial over I1 factorial times I2 factorial times U1 to the power of I1 times U2 to the power of I2. I can write this much more compactly by just saying sum coefficients B sub multi-index I times Bernstein polynomials multi-index I power 2 of a multi-argument U, okay? And then just say the vector norm of this multi-index I is 2. Where's the parameter space now? The parameter space is now a tuple U1, U2. Where does this U1, U2 come from? Again, I'm just after representing this curve. I'm just using these three sticks. I'm using just one index and one parameter in the first notation, x, x0, x1, and I just use one index to number the coefficients. As soon as I go to a barycentric calculus, I have to write every point on the x-axis as a combination of the two endpoints. Therefore, I need all of a sudden two barycentric coordinates. By representing an arbitrary x as a combination of the left point and the right point. Therefore, when I do this transformation from standard notation to barycentric notation, things become ugly. But they do not really become ugly, they become very beautiful. You will see that they become beautiful when I talk about triangles. But when I do that, I have two arguments. I also will have to deal with two indices, no longer just one index, but two indices. So therefore, index 1, index 2, index 1, index 2, index 1, index 2. The first one starts with the degree of the polynomials with 2 and goes down to 0. 2, 1, 0. The second one starts at 0 and goes up to the degree 0, 1, 2. Okay, that's the way how that runs. It's a pattern. But the curve, when you actually evaluate this curve, you get the same curve, of course. Just a change of notation. Where is the parameter space? Parametrization. The parametrization is now happening on a line in this U1, U2 parameter space. But it's still just a line on which I evaluate. This line is U1 plus U2 equals 1. Okay? And so when I run on that line in this direction, then I will run on this curve in this direction. Now I do it for the triangles, and for the triangles, everything will become much more intuitive and easy to understand. 2D case, triangular case, and that's where I will stop. X, Y, and F. So I have to start with a curved patch to begin with. We have something curved, a beautiful quadratic patch. So this triangular, curved triangular piece lives above some kind of triangle in the xy plane. These are the sides. I call the sides corner 1, corner 2, and corner 3. These are my function values at the corners. And if this is a quadratic patch, then its boundary curves have to be quadratic curves, those types of curves. Each quadratic curve requires 3 control points. And I'll just tell you that one will live here, the other one will live here, and the other one will live there. So you have this polygon defining that curve, this polygon defining that curve, and this polygon defining that curve. So you have 3 quadratic curves, 3 parabolae defining the boundaries. So you have these additional Bezier points. And so this network I can establish there is called the control net or control mesh of that quadratic patch. So the underlying patch is this nice, happy little patch that lives right here. I think you get the idea, right? So there is a smooth curved patch living in space, and it has this tent above it, and this tent consists of 4 triangles. 1, 2, 3, 4. 4 control triangles. The whole mesh is called a control mesh. And this entire patch lives above a domain triangle down there. So now comes the numbering of these things. These things, these circles or these bullets, are the control points. Now, in the case of a patch, I have to go to a triple index. I'm sorry for that. But this guy will now be called B2, 0, 0. This guy will be called B0, 2, 0. The one in the back will be called B0, 0, 2. And the others, of course, I have to play the game with the 1, 1 indices. So this will be B0, 1, 1. This guy must be B1, 0, 1. And this guy here is, well, the other one, the other combination, the other possibility you have. Now, this patch will be living over a certain parameter space. The patch has to be thought of as a triangle that I deform in space. The patch, this thing, is a triangle that I deform like a sheet of metal in space. So the undeformed piece is my parameter space. It's a triangle that lives in a parameter space called U1, U2, U3. So these are the base points, 1, 1, 1. And this triangle is the triangle or the plane U1 plus U2 plus U3 equals 1. And this triangle now gets deformed into the triangular patch. When I do that, I constructed triangular patch. Then I get this function or the patch, which depends on U1, U2, U3. And that guy will be a combination of I1 plus I2 plus I3 being 2, I1, I2, and I3 greater or equal 0. And the coordinates are BI1, I2, I3 times 2 factorial over I1 factorial times I2 factorial times I3 factorial times u sub 1 to the power of I1 times u sub 2 to the power of I2 times u sub 3 times to the power of I3. Okay, but again, in compact notation, you can just say this is the sum of B with the multi-index I times Bernstein polynomials I of degree 2 with the multi-argument U. Okay. I know this was very quick and very fast, but this is the notation for triangular Bernstein-Bezier patches. And there's no way around it, but we have to use it. Ultimately, this will be a beautiful way to handle with triangular pieces. It's a much better way to handle it than writing these things in terms of f of x and y. Okay? All right. So far, so good. Bye-bye for tonight. Kevin, I see you Thursday. This is it. We can stop.